Robotics engineers once believed that climbing smooth surfaces was impossible for machines. Glass, steel, and polished walls were considered the final bosses of robotics, places where no robot could grip, anchor, or maneuver without slipping. But nature had already solved this problem millions of years before human beings even knew what friction was. The solution didn't come from claws, glue, or suction cups. It came from an animal that defied gravity every single day. An animal that walked across walls as if physics didn't apply to it: the gecko. Scientists studying gecko feet discovered something mind-bending. These animals don't stick to surfaces the way we imagine. There's no glue, no moisture, no suction. Instead, their toes are covered in millions of microscopic hairs called setae, and each of those hairs branches into hundreds of even smaller structures called spatulae. At such a tiny scale, these spatulae interact with surfaces using van der Waals forces, atomic-level attractions so small that humans never even feel them. Yet geckos use them to cling to almost anything. They can hang upside down on smooth glass, run across ceilings, stop instantly, pivot directions, and detach with zero effort. It looks like magic, but it's pure biological engineering. And for roboticists, this was a breakthrough waiting to happen. When researchers realized how gecko-adhesion worked, they attempted the impossible: replicate it. But copying nature wasn't easy. Human-made materials couldn't match the gecko's microscopic architecture. The spacing had to be perfect. The angles had to be precise. The flexibility had to mimic a natural toe pad. Any small error made the synthetic material useless. But after years of experimentation, engineers finally created something extraordinary: a synthetic gecko-adhesive that worked on walls, ceilings, glass, and even dusty surfaces where normal adhesives fail. This wasn't tape. This wasn't glue. This was a new category of material: dry adhesion inspired by gecko feet. Suddenly, robots could do something human technology was never able to achieve: climb smooth vertical surfaces with no power-consuming suction, no chemicals, no magnets, and no residue. And the world of robotics changed overnight. NASA began developing gecko-inspired grippers for space missions. These could attach to satellites, repair equipment, and anchor astronauts in zero gravity without relying on mechanical clamps. Search and rescue robots gained new mobility, able to climb into collapsed buildings and reach places humans can't. Medical robots began using gecko adhesion to grip delicate tissues during surgery. Even warehouse robots started using gecko-inspired pads to lift fragile objects without crushing them. But the most astonishing development came when engineers created a full climbing robot entirely inspired by the gecko. It could run across glass walls like a tiny lizard, using synthetic setae that activated and deactivated adhesion with tiny mechanical movements. It didn't need suction pumps or power-hungry systems, just physics, just the same natural forces that geckos mastered long before robots existed. One of the breakthroughs that shocked scientists was how geckos detach from surfaces. They don't peel, they don't pull. They simply roll their toes in a precise motion that instantly breaks the atomic attraction. Engineers copied this too, building robots with toe pads that lock and unlock on command, making climbing smooth walls feel effortless. This natural mechanism became the core of new robotic systems in factories, construction sites, laboratories, and even military applications where silent, smooth climbing is essential. The gecko foot didn't just solve adhesion, it rewrote the rules. Because once robots could climb walls, everything changed. Surveillance bots gained new vantage points. Inspection robots reached dangerous vertical structures without humans risking their lives. Engineers designed gecko-inspired gloves that let human beings climb walls like a natural superhero. Scientists created gecko-inspired drones that could land on glass skyscrapers and cling without slipping, even in wind. The gecko didn't just inspire a new material. It inspired a new generation of robots that move the way nature perfected millions of years before us. Robots that grip without force, climb without suction, and hold without glue. And yet, even with all this progress, we still haven't matched nature's perfection. A real gecko toe can adjust grip thousands of times per second, responding to the smallest shifts in weight and angle. Its microscopic hairs self-clean. They reset automatically. They work in heat, cold, dust, humidity, and complete dryness. Human technology is still catching up. Every time engineers think they've mastered the gecko's secret, nature reveals a deeper layer of complexity. And that's the lesson biomimicry teaches us again and again. Humanity is not inventing new technologies. We're discovering what nature built first. The gecko foot isn't just a biological wonder. It's a blueprint for the future of robotics, space exploration, wearable technology, and engineering. We didn't rewrite robotics. The gecko did. We're just learning to read its design.